So this is the 1992 Electricity and Magnetism AP problem. Part A is asking you to find where the magnetic field inside the loop is directed. So since you know that the current is flowing this way, and it is also decreasing with time, you know that the field would go out of the page inside the loop, but it would be decreasing. So obviously this loop would aim to oppose that change and aim to keep it going out of the page. So that's the answer. It would look something like this. So part B has two parts, and the first one is asking you to find an expression for the magnetic flux as a function of time. So you know that this is the equation for current, and you know that this is the magnetic field dependent on the wire. And essentially what you do is you plug in this I, which is the current of the wire, into here, and you have this. So since you have to find the flux for this entire loop, you also need to know the area, and essentially for this law you would have to multiply it by the B field, which changes with R, and that's why you have to plug in this for dA, since this basically is C times the change in R, which is this area here, which is basically any radius between A and B. It's the distance from this wire. So take this integral, add in those limits, and then you plug that in here along with C dr. So you have C mu naught alpha times the rest of this equation over 2 pi r times change in R. So this is basically going to be constant, even so is time, since you're talking about a specific time. But what you are looking for is for the change in R. So since you have dr over R, you have the property, so you have this property, and you simply divide the top by the bottom, and you have this equation for flux. Now part 2 is asking you to find the induced EMF in the loop. So you use this law here, and this is the change in flux with respect to change in time. And this is flux, and this is change in flux with respect to time. It's negative since this would aim to oppose the change in flux. So essentially all you have to do is take the flux and basically take the derivative of it with respect to time. So you have this as a result, you have this equation, you just plug it in here, and everything else gets to be taken out. So you just have this area here, and you're deriving it here. This is obviously just 0, and this is obviously just B. And you multiply it here, and you have this answer. Part C, part 1, is asking you to show the direction of the current when this right here is less than 1. So when it's less than 1, we know that the current would be positive, and the wire is right here going this way, so this direction would be positive, meaning that the magnetic field would be going out of the page, and it would be decreasing, since as time increases, this constant increases, and then eventually this would be negative. So since it's decreasing, the current would have to go out of the page in order to suppress that, so it would be going this way. For this, however, it's greater, so it's already negative. So it would be going that way, but since it's increasing, even though this is going this way, this would still have to oppose it by going out of the page, so the current would be in the exact same direction. Part D is asking us to find out whether there is a net force on the loop. So this starts at t equals 0, so right away we know that if we plug that in here, the current would be equal to the constant alpha. We know that F equals ILB, the force of the magnetic field, and we know that the length would be c, which is just the length of this top thing. Since we really aren't paying attention to these sides, because they cancel each other out, this length is the only one that matters. So the force of the bottom one would be the current times the length times the magnetic field, which uses the previous equation, and A as the radius. So since we know that the current at time 0 would be flowing counterclockwise, we would know that the bottom would be pulled down towards the wire. So for the top, the only difference is that the radius is B, and since here it's going this way, the wires would try to separate, so it would push it up. So the forces are going opposite each other, so you need to find the difference. But since this is really only asking us whether it's going up or down, if there is a difference, then all we need to know is that since B is greater than A, and they're being divided by these constants, we know that the F top would be less in magnitude than F bottom. So we know that the net force would be going down.